Good afternoon. I'm Viraj Shah, an undergraduate student at Vijaya in India. I'm here to present some work and ideas around building more accurate models of code performance, specifically for the use in training of machine learning models for machine learning guided optimization. So I'll begin by building some background on the topic that should lead us to the ideas behind what we're trying to do. So first of all, why do we need these cost models? The more direct approach to measuring the performance of a code snippet in terms of either latency or throughput would be to time their execution, but this isn't really feasible because real measurements are expensive and tedious to obtain. It takes a significant number of benchmarking iterations to obtain a consistent, reliable measure of performance, without which training it's a lot more complicated and less deterministic and overall, well, worse. Care needs to be taken while setting up and maintaining the benchmark environment as well if you go down that route. And since cost models determine the reward signals, and it is crucial that the predictions of the cost model are accurate and made effectively, as the quality of the reward signal directly affects the quality of the decisions made by our models. And so the cost models used for register allocation eviction in upstream LLVM, it's a fairly simplistic linear model which scores machine functions based on certain types of machine instructions like load, stores, copies, how many of them there are per machine function or basic block. And then you adjust them for basic block frequencies to get a score or some idea of how good the generated code is. But this cost model it's good enough to produce models capable of replacing heuristics for register allocation because it captures the right information specifically for informing decisions related to register allocation. But it is not a particularly good predictor of how well the code snippet performs concretely. Some available state-of-the-art static analysis-based and learned cost models designed to make those concrete throughput predictions are quite decent at just that, but they also have some glaring weaknesses that we really wish to overcome. So these models still leave some improvement to be desired, specifically in certain situations. All of the cost models we talk about, they make idealistic one-size-fits-all assumptions about the execution environment and the runtime behavior of the code. So we miss out on modeling important runtime events such as cache misses and branch predictions, which they impact how well a piece of code performs, and the performance estimates end up being set off by, multiple orders of magnitude, say from several cycles to, a few hundred cycles. And so to formalize the problem we are trying to solve, and hence the goals of this work, we want to better model the execution environment in order to systematically apply MLGO to more optimizations, or simply put, build better models for MLGO training. Since the runtime behavior we care about is extremely difficult to model entirely statically, we want to augment models by including additional runtime or profiling information such as additional PMU data or LLC misprobabilities, branch mispredictions, which should nudge the models towards figuring out how the program behaves at runtime. So we're looking at using a learned basic block cost model and augmenting it to be able to use this extra information about what kind of non-ideal behavior we're going to see out of the block being processed, which involves, for one, building a data collection pipeline that covers additional runtime information, to modifying the basic block cost models to allow processing this data, and then finally modifying the training and inference processes in terms of learned cost models to actually make use of this data. The goal of this project is to move from static analysis closer to some more dynamic models that better represent code in the way that it actually executes. And we can measure how much better or worse a cost model is using standard measures of accuracy. But there are also a few more metrics that are more relevant to MLGO training. For example, since the block performance drives a reward signal, how close the ordering of blocks by estimating performance is to the ordering of blocks by true performance is a good metric which can be quantified by rank correlation metrics like Kendall's tau or Spearman's rho coefficients. So with the aim and motivation clear, we can talk about some ideas towards a solution. To keep the scope of the problem reasonable at an initial stage, we focused our efforts on to only modeling cache misses while keeping ways to extend to other runtime events, other things like branch miss predictions and so on in mind. So the question is, what kind of runtime information would be most useful, and how would we use that information to improve our predictions? For measuring most kinds of runtime effects, we can utilize performance monitoring events that are provided by the hardware through performance monitoring units. For example, we have like Intel Skylake PMUs that support things like MLGO retired.l3miss, which is one of the many events it supports related to cache misses. So we can directly hook into these performance counters using perf on Linux or through libbfm, and we can effectively collect cache miss frequencies or probabilities for individual instructions, which is a good start. Then comes the second part of the question from the last slide, which is how would we use that information to improve our predictions? The simplest way of doing this would probably be to associate cache misses with a fixed penalty and add an overhead linearly related to the number of cache misses and those other statistics that we either collected from the performance counters or calculated using them. And to see how practical this is, we experimented with some memory access patterns by setting up a number of micro benchmarks controlling the caching behavior to some extent by forcing some instructions to cache miss by invalidating the caches and having a different number of instructions which could possibly cache miss and a bunch of other variables. This would allow us to test the correlation between the numbers or frequencies of cache misses and the throughput cycles. That is to say, whether we can directly add some function of the number of cache misses and cache miss related statistics to a latency estimate where we assume that there are no cache misses and arrive at a decent estimate of the overall true latency of the basic block. But we learned that the extra overhead from cache misses cannot be modeled well using only cache miss counts or frequencies, and the context of the code or the specific instruction is important. For example, given some access pattern and the number of cache misses happening, we can use a found cost per cache miss to get a reasonably good estimate of performance. But this found cost per cache miss doesn't really generalize to any other access patterns, or it's quite situational, which opens up the possibility of first classifying a memory access into one of these categories and then using a found cost per cache miss value to estimate performance. But then that's a whole other can of worms with classifying memories not being classifying memory accesses not being straightforward, but there being questions of how many categories there are, what they are, and how we might differentiate between them. And this brings us to the current approach, supplying learned cost models with added context about the instructions by annotating them with the collected runtime information. The learned cost model should be able to incorporate that additional information within its internal rich representation or embedding vectors of the instructions of the enclosing basic block. We have a few options for the learned basic block cost model that we could extend to supply with cache miss information. Notably, we have RNNs or sequence models taking in instruction streams like HTML, and we also have GNN-based models that represent basic blocks as graphs, like Granite, which builds graphs representing basic blocks where things like instruction mnemonics, prefixes, and operands represent individual basic blocks, and they're represented by nodes, and the connections between them, the edges, represent the relationships between those operands, mnemonics, things. Granite Granite has a more detailed representation and is better suited to learning patterns in code and to be able to understand the underlying memory access pattern. So that is what we chose to extend. To incorporate this extra runtime information into granite-like models, we can use it as part of computing the embedding vectors for instruction nodes by ordering individual instruction level runtime metrics and then appending them to the ends of plain embedding vectors made without taking any runtime effects into consideration, and then letting the base model have those extra uh, embedding elements sort of flow into the rest of the computation graph, and well, in general, just handle how those values actually end up being used in the performance estimate. All of this works in theory, but practically building a dataset that is large enough to train such a model with cache miss or runtime information in a way that is representative of how the program actually behaves is a huge task in and of itself. Since while basic block latency ground truths can be collected on a basic block level of granularity, but whether an instruction will cache miss or not usually depends on the overall program state and whatever came before this particular basic block. And the way we are looking to get around this is by having something like a fine-tuning step while training, which uses a sub-data set with runtime information, while the rest of the training process uses a much, much larger data set that doesn't really need to have this extra information. So this is the stage this work is currently at, which is unfortunately just short of having knowing concretely how much better these models are. And as for future directions, the immediate next step would probably be to expand to the other runtime behaviors we set aside earlier, like branch mispredictions. Aside from that, another way to expand on existing learned basic block cost models to improve their accuracy in these situations would be to feed models with more context about the basic block, such as something like a call chain or an execution trace, so that they can potentially figure out more about the underlying memory access pattern. For example, if the model knows if a block loops on itself most of the time and then accesses the same memory over and over again, it's not very likely to incur any significant cache misses. So that's it for this presentation. Thank you for your attention. Any questions?